Every electrical appliances that we have in our house may have some kind of thing written on it. If you have closely noticed, they have their power ratings. Maybe 9-watt electrical bulb or 100-watt electrical bulb. Every electrical appliances must have been rated with such kind of values. What these values are? As I was telling you earlier, these are actually the power ratings. Power is nothing but defined in mechanics as the work done per unit time. It means that any appliance is doing certain amount of work or converting certain amount of electrical energy into any other form of energy. Thus, doing so, how much energy transfer or transformation that particular appliance is doing within a second is known as its power. Today, we'll try to understand mathematically how we can define electrical power and how we can relate it the values or the parameters in electrical circuits. If you recall, in electrical circuits, we have certain values. We defined it by current I, by voltage V, and also by the resistance R. Let's try to generate a relation. How can we do that? Let's start with the work done first. How we define work done? Work done, if I write it here, work done. What is work done? So work done in mechanics, we know it's very easy to move any body, how much force we are applying by moving a certain distance, simple F multiplied by the distance or the displacement comes out to be work done. In electrostatics, we know about the work done that moving a charge, how much force we are applying, that comes out to be the electrical work done. Now, for power, if I write here electrical power, we can define it as the work done by per unit time. Let's say this is the time. Now, electrical work done that we are doing, as I already told you, it's something that we define while moving a charge in a certain electrical field. That electrical work done is nothing but Q multiplied by V. Here, in place of Q, you can define in terms of Ne, that is the number of electrons flowing. Let it be. So Q multiplied by V, here V is nothing but known as the voltage that we are applying in any electrical circuit, or the net voltage if there are multiple cells or batteries. This is, we define the work done. Why I put it in the electrical power? This time just denote the electrical power with P. P equals to W. In place of W, I can easily put this QV by T. This comes out to be power. Now, we know the unit of work done. Unit of work done is nothing, but we know it's joule. It's joule, unit of work done. So, joule per second is nothing but the power, and we call it as watt. We gave this unit to respect James Watt. Now, QV by T. What this Q by T is? If you recall all the previous classes, you will understand that Q by T is nothing but actually the current flowing in any circuit. Thus, we can simply write this P equals to IV. This is the equation that we will be using, for power calculation in any circuit. Any circuit. Now, what else I can do with this equation? Let's try to play a little with this equation. Can you please recall the Ohm's law? Yeah, we derived the Ohm's law in the previous lectures, in which we come to know about that we have a certain relation between the electrical parameters that are current, voltage and resistance. It was nothing, V equals to IR. That voltage and the current are directly proportional, and voltage is exactly equal to the multiplication of current and the resistance in any circuit. Now, if I try to substitute the values so that I can understand a relation for power in terms of resistance and the current, let's try to do that. From this Ohm's law, what I can write? I can write V in terms of IR. What I'll be getting? I'll be getting P equals to I multiplied by I into R. That is I square R. So this is the expression for power in terms of current and the resistance. Now we have one relation for power in terms of voltage and current. This is our first relation. We have the second relation in terms of current and the resistance. Let's try to solve one more relation in terms of voltage and the resistance. It's also very easy. Again, we just have to see this equation P equals to VI and replace the Ohm's law in such a way that we'll get the relation in terms of R and V. So I have to remove this I. In place of I, what I can write? If I substitute this in a form, I can write I is nothing but V by R. Let's try to substitute this expression in the first expression. What we'll get? We'll get our third expression. Let's write it out here. P equals to I is nothing V by R. So I is nothing but V by R and this whole multiplied by V. So we'll get P equals to V square R. Now, let me write all the three things together for your reference. So we have P equals to VI, first relation, that is equals to V square by R and that is equals to I square multiplied by R. So these are the three expressions we have that are relating the electrical parameters with power. Now, how to understand it? Let's try to understand it with an example. Let's say we have a household. In our household, we normally have the voltage supply of 200 volts. I am taking totally random values. 200 volts. Now, let's say we have two bulbs. Two bulbs having 200 ohm resistance. 200 ohm. This is a symbol of ohm resistance. And now, if I ask you to calculate the power, how will you do that? Let's try to understand. So, let's say we know power. Power is defined by V square by R. In terms of resistance, if I am calculating V square by R. So, we have the power consuming devices and that are 2. Let's start with power 1. Power consumed by 1 bulb. Power consumed by 1 bulb. 1 bulb. Power consumed by 1 bulb. So, it comes out to be P1 is equals to V square by R. V, I already wrote it here as 200 volts. So, 200 multiplied by 200 upon R. R is what? 200 ohms. Let's write it out here. R is here as 200 ohms. Now, let's say 1 200 got cancelled and we get P1 is 200. Now, this is the power consumed by one bulb. What is the power that will consume by another bulb? Obviously same, because both bulbs having the same resistance. So I can write P2, that is the power consumed by the second bulb, is also 200. Let me write out units as well, watts. This is also watts. Now, 200 and 200, the total power consumed by the house, let's say is 400 watts. Now, if you have noticed your electricity bill, you must have found something written in terms of units. What these units are? Actually, we measure the value of power in usually kilowatt hours. 1 kilowatt hours we have defined as 1 unit and then we calculate the electricity bill with reference to that. Let me show you how. Now suppose in our case we got the net power as 400 watts. We are defining a new terminology for it that we are calling kilowatt hours. kWh. This kilowatt hour is equivalent. Now, let's say in my place the electricity bill is something like 20 rupees per unit. And these two electric bulbs are continuously on for let's say 2 days. Now, in order to define this power 400 watts in term of kilowatt hour, first I'll be converting this power watt into kilowatt. Kilowatt. To do so, I just have to multiply by 10 to the power minus 3. So I'll get the power as 0.4 kilowatt. Okay. Now, this is my power. And if these two bulbs are continuously on for 2 days, I can convert these 2 days into hours. What I'll get? I'll get easily 48 hours. Multiplying this 48 by 4, we'll get to multiplying this 48 by this 0.4, we'll simply get 19.2 kilowatt hours. This is the unit of my power. I got it in kilowatt hours. So this is exactly equals to 19.2 units of power consumed. Now, if the electricity bill, as I mentioned here, is 20 rupees per unit, and you will ask me what will be the total amount that I have to pay, I just have to multiply 20 with this. What I'll get? 4, 3. And we get 384 rupees as my total bill. I simply multiplied this 19.2 with 20 and I got 384. Well, that's all for today's class. I hope you got all the concepts that we have discussed about the power, kilowatt hour and units. We'll meet again in the next video. Till then, stay connected.